Okay, good afternoon, everyone. Thank you so much for being here. We are actually at the last session, session 11, on pattern recognition in agriculture, very interesting topics. We have had two of our presenters presented in the afternoon and morning session before lunch. So we will be starting with paper ID 57, Deep Learning for Root System Extraction from Barley Plants, presented by Alessandra Lumini. So I'll give the mic over to Alessandra and he can start.
Okay, thank you. Okay, welcome everybody. I represented this work about deep learning for root system extraction. This is a collaboration between the Department of Computer Science and of Agriculture of University of Bologna. At the Department of Agriculture, they are studying genetic variation applied to barley seedlings. And the goal of the research is to verify whether genetic variation corresponds to greater seed resistance to atmospheric conditions. This is why they photographed a number of in vitro grown barley seedlings to evaluate the characteristics of the roots. They provided us with a data set, including hundreds of these images. And the goal of our research at the computer department is to segment the seedlings from the background and automatically extract some measurement, such as the number of the roots, the average and maximum length of the roots, the width of all the roots, and other. For our research group, this was the first experience with root image segmentation. Initially, we tried to apply our expertise, developed mainly in the field of biometrics and biomedical imaging. However, the first attempts were unsuccessful because this data set is quite complex. It includes images with a high number of roots, with high variable background, low contrast, and so on. We also tested some root analysis system from the literature. Some of these tools are cited in this slide. ChronoRoot, for example, is a root system extraction from a time sequence. RootNav is a root system extraction from image plants, from image of plants. Both of these systems were trained on different data sets, very different from other, and failed to segment our images. For this reason, we try to address this problem by proposing an innovative approach. Our data set consists of 200 high-resolution images, but without any ground truth, so they are not segmented. Specific issues of the data set includes the presence of various background texture, variable light conditions, overlapping roots, and manually taken images that require alignment. So the proposed approach starts with a preprocessing step, which involves extraction of the raw area of the image through case detection algorithm, bounding box extraction, and alignment. Then a second segmentation phase to remove the background and highlight the roots. The next step is the representation of the root system through a skeleton graph, which highlighted the main points, such as tips, seed, and some intermediate points. And the final steps consist of root system extraction, where each root is represented by a spline to count the root, measure length, and extract other measurements. Briefly, the preprocessing steps consist in aligning and cropping through mask extraction. The result is an image with the same resolution, but cropped and without the black background and all non-interested part. The next step involves a segmentation, and this is certainly the most complex part of this project. After numerous failed attempts with a traditional method, we decided to use deep learning techniques. The problem with using deep learning is obviously the absence of ground truth for this dataset. So we collected a shared data set from the net that includes 3,000 images, very different from ours, to which we added a dozen and annotated images from our data set. And in this work, we compare 4 different architectures from selected from the most used in the literature. The result, after 100 epochs of training with this collected data set, was still not acceptable. So some of the resulting masks were subjected to a post-processing phase to thin the extracted root and trim any protrusions. From this set of images, we manually selected the best one to use them as a second phase training set for a second round of training. So we had 2 rounds of training, the first of 100 epochs, the second of 50 epochs. The result of this segmentation phase and the comparison of the architecture is shown in this slide. We compared 2 different kinds of architecture. UNet and DeepLab are architecture based on CNN, the most used maybe in most of medical imaging problems. The other one, HSNet and CAFNet, are more recent architecture based on transformer. As you can see from the table, the best results are the one obtained by CAFNet. We reach intersection over union performance greater than 70%. That is quite good, as you can see from the image. CAFNet is also the most complex architecture in terms of number of parameters to train and inference time. But we decided to prioritize performance in this work, even because the inference times for a single image are less than a second, so totally acceptable. So we use CAFNet in the next step of our method. The following step is the construction of image skeleton using media access method, followed by a regularization step to remove any possible protrusions or small branches. We use the SKNView library for graph representation. The result is a graph whose nodes corresponds to tips, I think in red here, the seed, green, and any bifurcation point. From this representation, we applied a method for root path analysis. The first algorithm that we tested is very simple, the shortest path that try to find the root, the minimum length root from each tip to the source, that is the seed. The second algorithm proposed in this work is based on the shortcomings of the first algorithm. This algorithm, called enhanced graph traversal, works as follows. First, all tips are extracted. Then all paths from the tips to the source are calculated, not only the shortest one. The shortest path is directly inserted as a solution. All the other paths, from all the other paths, we selected only those that grow monotonically versus the seed, and inserted those paths into a list for a second evaluation. And then from this list, all paths that do not overlap more than 80% the one already selected are selected again to be in the final solution. This algorithm, as we will see later, allows us to achieve better coverage of the present route, mainly in images where there is a lot of intersection or overlapping among different plants. The final step of the method concerning saving the result into a format that is RSML format. This format is based on XML and is used to facilitate the saving, the sharing of root data, as well as interoperability between different analysis programs. So there exists several programs that use RSML to extract some information about the roots. Here we are at the experimental test. We built another test set by hand annotating 10 images for a total of 24 plants. This is a small data set because the annotation work is very long. And to evaluate the effectiveness of the tested approaches, we consider metrics such as the total and maximum root length, okay, total length of all the roots of a plant or maximum length of a single root, the area covered by the root system, shown in this figure, the outer angle, which is the angle between the most left and the most right root, and the tortuosity. To evaluate the quality of these measurements, we defined a normalized relative discrepancy, which consists of evaluating the difference compared to manually extracted ground truth. The compared approach concerns into the two extraction algorithms presented before, so shortest path and enhanced graph traversal, and a method from the literature that is RootNav 2.0, that is the automatic version of the RootNav approach, that is an approach published a few years ago. This last method has been fine-tuned on our dataset, but using only the small dataset that we have manually labeled. And the results show that the new method called enhanced method achieved the best performance in most indicators. And visually, it is also noticeable that it is the most accurate method because it is the one losing the minimal number of roots. However, the proposed approach is not error-free, as evidenced in the image that there are some missing roots, and this shown here is one of the simpler images. For the more complex one are difficult to analyze even manually. In conclusion, we need a lot of work for the future. Here we presented the main step of the algorithm that are segmentation through deep learning and skeleton construction, and the two new path analysis algorithm. Possible area of improvement include better identification of the root structures in case of overlap and intersection with a neighboring plant. We are creating a larger manually annotated data set to improve both the segmentation algorithm and the path analysis algorithm. We have also created an ad hoc tool for manual image annotation that we are writing a paper about it, and we will present it for the conference. I think that it's all for today. Thank you for your attention, and I welcome any questions that you may have about this work.